Welcome to Simplified. My name is Gurjot.
And my name is Michael.
And this is episode 8.
In this episode, we spoke to Jing Wang.
We spoke to Professor Jing Wang, who is an assistant professor in the Department of Environmental Engineering here at ETH.
Particularly, he focuses on particles.
He focuses on air nanoparticle emission.
And how that can kill you.
Yes.
Let's find out.
Let's find out.
So I had my bachelor degree from Tsinghua University in Beijing. So after I did my bachelor degree in Tsinghua, then I went to University of Minnesota. So at University of Minnesota, I did my PhD, and then following that, I worked for a number of years at University of Minnesota. And then in 2010, I moved from University of Minnesota to ETH, and so here. So I'm at the Institute in Environmental Engineering, and so my specialty is in the field of airborne, so the airborne pollutants. So we do a lot of studies, for example, on the emission measurements, what are coming out, what pollutants are being emitted. Usually my focus is mainly on the anthropogenic processes, so the man-made pollutants and how much they are being emitted. And then this is, first of all, we would like to know the emission and the release, and we would like to characterize these emissions. So what's the concentration, what's the chemical species, what's if these are particles, what's their particle size, what's the what's the transport properties in the environment, what's the exposure risks, how much of these would end up if humans are being exposed to those, and how much of this end up in the human's lung, what's the risks for these pollutants for the environment and for human health. And then after we understand this, we would like also to have control, to develop control technologies so that we will reduce the emission of these pollutants into the environment, so that we can protect the human health and protect our environment.
Can you start by giving us an overview of how significant this air pollution problem is in the world?
Well, the air pollution, the problem, if you look at the global, the WHO, the World Health Organization, they give a list of the top factors which lead to mortality. There are two factors. One is outdoor air pollution, so the ambient air. The other is indoor air pollution. So both of these are ranked quite high. So I don't remember exactly the number. So sometimes probably the indoor air and outdoor air, this is usually ranked somewhere around 15th or 17th, something in this range. So they contribute to the mortality. And if you have this, and there are a lot of studies showing that the mortality, the extra mortality, can be linearly correlated with the amount of the airborne, the fine particles. So in the U.S., so in the U.S. earlier studies, the so-called six city study, so they look at the airborne particle concentration, so the so-called PM 2.5. So the particles less than 2.5 micrometer, so those particles floating in the air called the fine particles. They look at the concentration of these particles and then correlate to the mortality of these cities, and then you can basically come up with a straight line. So the higher the airborne pollutants, the more people die.
Wow.
So PM 2.5 and also PM 10, this is like the keyword that comes up in news reports all the time.
Yes.
So you said PM 2.5 is any particulate matter of the size of 2.5 times micrometers.
2.5, that means any particle is less than 2.5 micrometer, and then you put all these particles together and you weigh them.
Is this a good measure? What does 2.5 micrometer have to do What do these particles do?
Right, very good question. So that is related to where these particles are coming from, and so basically you need to understand the typical size distribution of the particles in the air. So the particles usually we in the ambient, the particles could have several different modes. You could have so-called the coarse mode. So these particles are usually bigger. So on the size bigger, 10 micrometer, 5 micrometer, or something like that. So these particles are usually from mechanical sources. For example, the dust on the road. You have sands on the dust. You have wind, and then these particles get suspended in the air. So these particles are usually rather big, and then they would not stay in the air for a very, very long time because if they are big, then the gravity, then they will settle down. And then there's another peak for very, very small particles. So these very, very small particles, one possible source could be chemically, they have a nucleation. So from gas molecules, you have certain gas molecules in the air, and then these gas molecules, they have a nucleation, and then from small gas molecules, they turn to particles. So this is from bottom up. And these particles could be quite small, so we call this a nucleation mode. So this nucleation mode could be quite small, down to around 10 nanometer, or somewhere around there. So then these particles, so we have this big mode, this very small mode, and then these very small particles, they can hit each other. Once they hit each other, they can form bigger agglomerates, they can grow, and also there are other particles. For example, the cars, you have emissions from the cars, you have combustion, these generate the soot particles. And so these particles, they can form agglomerates and grow. These particles can become bigger, up to several hundred nanometer, and then they further grow somewhere around 1 micrometer, 2 micrometer. So then there's a cutoff. There's a cutoff. There's a big peak for the big particles, and then this peak, we call this accumulation mode around 1 or 2 micrometer, and then the very small nucleation mode. So these two smaller modes, so they are usually below 2.5 micrometer, and so these particles can stay in the airborne form for relatively longer time, and you inhale these particles can go relatively deep into your lung. So that's why a lot of the health studies are giving us the indication that the concentration of this PM 2.5 is correlated to the human health.
If I understand correctly, so lots of smaller particles of the order of nanometers, which is 10,000 times smaller than a micrometer, so they agglomerate together, and the size that they cut off at is about the size of 2.5 micrometers or less. And then we inhale these particles together and they go deeper in our lungs. So is this particle size or are these particles worse than cigarette smoke?
Cigarette smoke is obviously one of the possible sources of the PM 2.5. So you have a very good question. That's, do all the particles behave the same? Mm-hmm. Do they all have the same adverse effects on the human health? The answer is no. So you have a very good question. So if you have some particles for example, sulfuric acid. So you burn something, you will have sulfur in the fuel, and then you have SO2, and the SO2 emitted, then SO2 in water, they will condense. So then this will form sulfuric acid droplets and things like that. So you could have soluble particles. So these are basically liquid droplets, and once you inhale them, so they will basically disappear. They will dissolve in water and dissolve in your body liquids. So these, if they are soluble, so usually, not in all the cases, but at least we consider their effects are not that severe. And some particles are inert. They go to your lung, they will not have significant effects. but some particles, for example, the heavy metals, this is known for copper oxide. These particles are known that they will induce they will have stronger toxic effects. So obviously heavy metals, they go to your body have no way to dissolve those, and it's difficult to get these particles out of your system. Another example is asbestos. So asbestos, has been banned for over 30 years in Europe. So these particles, so it's not just we are talking about PM 2.5 as if all the particles, you can describe all the particles with one diameter, but that's clearly not true. You have these fibrous particles which is quite long, but the diameter is small, so they can go, when you inhale those things, they can go deep into your lung, and when they go to your lung, it's difficult to get those things out. So they can cause very severe health damage. For example, we know that the asbestos can cause lung cancer.
And all this is direct causes of deaths from these air pollutants. But in addition to this, there's a huge problem that it ruins the environment. Is this also?
Right, so there are certainly direct causes and indirect effects as well. So obviously when the concentration is very, very high, these things will cause a lot of different diseases. Most of these are pulmonary diseases related to your lung. And once you have this in your lung, and then you have the mechanism, this will also cause cardiovascular diseases, so for your heart-related diseases. And there are also studies showing that this can the particles going into your body can translocate into different organs. They do not necessarily stay in your lung. They might be able to penetrate through your blood system to go to your different organs. So, but these are all, we are all talking about the direct health effect on human. And then the secondary effect, of course, then you have the environment for all the animals, the effects on plants, and the effects on general welfare. So people see, wow, this place, if I go outside, I see so much of dust, like in China. Then obviously the quality of life, you don't, even if we are not talking about direct health, but the quality of life, that's adversely affected.
Could you tell us briefly what the sources of these nanoparticles are? Because I read on your webpage you focus on airplane emissions. So why do you particularly focus on airplane emissions? And before that, what are the sources? Right.
So there are a lot of sources we already mentioned. We already mentioned a lot of these sources. For example, transportation. Transportation nowadays, especially for developed countries in the city, transportation is one of the major sources. So there are a lot of regulations you see for your car when you're driving a car. The Volkswagen people know this very well, or maybe they don't know this very well. So these regulations, you cannot emit the limit are set. You cannot be emitting higher than that. So that's exactly for this reason. You know that's because transportation is part of the sources, a significant part of the sources in the cities, and also. You have to have power, and you have to this power generation. Of course, you could have hydrology in Switzerland. You know, the hydropowers is a significant part, but a lot of other countries, for example, in China, they burn, as we already said, they burn a significant amount of coal. You could burn petroleum. You could burn natural gas. So now all these are energy, and you burn something. And then ideally you burn you don't have incomplete combustion. You only get CO2 and water, but normally that's not the case. You burn something, and in the fuel you will have sulfur, you will have chlorine, and all these things. So you have all different types of emissions, and then these emissions will come out. So sometimes these emissions come out directly as particles. The black, when you burn a candle, you can see the black smoke coming out. So directly you have particles. You also have gases coming out, SO2, NOx, NO2, and organics, so these things. And after certain reactions, so they can also be turned into particles. So all these things contribute to the particles. So
why do you focus on airplane emissions specifically?
So the emission standards for the diesel engines, for the cars, for the buses, this is very well known. So Euro 5, Euro 6, these are landmark standards for the cars, for the diesel engines. And what is not being completely finished is what's the standard for an aircraft engine. So then this part, we are doing the research, we are providing the data for the, so this project is mainly sponsored by the Swiss Federal Office for Civil Aviation, and this international standard. Of course, for aviation, it doesn't make sense for Switzerland to make a standard. All the aviation standards are international standard. This is governed by the International Organization of Civil Aviation, so ICAO. This is the governing body. So they have about over 100, so somewhere between 100 to 200 members. So these are different countries and regions where you have aviation. So then this aviation standard, so just this year in February, the International Association of Civil Aviation, so they just passed the resolution. There will come this new standard based on the non-volatile particulate matter. So in the future, by 2020, all the passenger engines used on the passenger airplanes will need to be certified according to this standard. So their emissions cannot be higher than a certain amount. So we are doing this research. We are doing the emission measurement. So to set the standard, you need to know what is the current situation. You need to know what is being emitted by the current engine. So we are doing this collaboration with SR Techniques. This is the company near the Zurich airport. So we go there and we set up our testing facilities. Then we measure what is being emitted from these aircraft engines. Then we provide this data for the international standard.
Do you also help coming up with the final standard?
Of course, we provide the database. Eventually, this is up to the governing bodies. In Switzerland, this is the Federal Office for Civil Aviation. In America, this is the FAA, Federal Aviation Agency. So then the representatives from these governing bodies, so they are the regulators. The regulator, their job is to come up with this standard. So our job as scientists, we provide the data, and we provide the data to them, and eventually this will be a negotiation between the regulators and the industry. If you put a standard, nobody can satisfy this standard, then it's not useful. If you put this standard too high, everyone can satisfy without any effort. It's useless. Yes. So then you have to have this you know what is the best technology now, and then so you know what is the possible limit, and then at the same time you also need to maybe the technology is still nobody is doing a good job, and then you're still emitting too much. So the end result is that in the ambient the concentration is too high. Then you need to push the standard down to make this situation better.
You mentioned certain consumer products also emit nanoparticles that are harmful for the air. What are you talking about? Aerosols found in deodorant cans? Could you
give us some examples?
Yeah.
Yes. So when we are talking about the air pollution and all these things, I have no intention to describe all the particles as bad particles.
Okay.
So there are a lot of, with the development of nanotechnology, we have a lot of particles. They are very, very useful. They have very, very good properties, and so they are at the forefront of the new technologies. So if you look at these buzzwords, the nanotechnologies, the nanoparticles, these are very hot topics. the Apple, they have certain, so you have screens, the screens, they use certain nanoparticles there for the color, and for the food industry. For the food industry, a lot of the color in food actually from these nanoparticles giving you the color. And for the paints you use on the wall for the sunscreen. People use sunscreen, huh? So you put this cream on your screen to avoid the sunshine. A lot of titanium TiO2, the titanium nanoparticles are being used in the screen. So because they can absorb the sunshine, so they can avoid the skin burn from these particles.
That's very interesting because I never thought nanotechnology had anything to do with nanoparticles. I always thought it was more robotics or something.
Like tiny robots
Yes.
that we design.
Yeah.
So nanotechnology is that essentially changing things on a very small scale?
Of course, the nanotechnology, you have to do something at nanoscale, huh?
Yeah.
So if you do things at nanoscale, the nanoparticle is one of the building blocks of nanotechnology. So you need very small features. You can also use very special nanoparticles for their very special properties. So one of the most well-known ones is carbon nanotubes.
Carbon nanotubes?
Yeah. So the carbon nanotubes, this is so the 2D materials, graphene. So you have one layer carbon atom. So this is 2D material. Then you roll it up. Then this is carbon nanotubes.
Okay.
Wait, carbon nanotubes are very small, like it's a shape that we can use to build structures on a very small scale?
Yes, right. So carbon nanotubes, usually you have the diameter of this tube. Usually, you can have single wall carbon nanotubes. So carbon is just, you can form a carbon structure. It's just a network. So it's a hexagonal structure. It's just a network. And then you can form a 2D. This is graphene. And then if you roll it up, then you have a tube. So this tube can be very long. So you can have a very long tube up to even longer than 10 micrometer, but the diameter can be sometimes down to 2 nanometer or 3 nanometer. So it's extremely long, and so this aspect ratio is extremely high. So because of that, you can have very special properties. For example, very strong mechanical property, and so this compared to its mass. For the same mass, and then this is the strongest material in the world. And of course,
is this the same technology behind carbon fiber that's used in automobiles?
Yeah, exactly. So carbon fiber, these are a little bit earlier. So you basically have carbon fiber is basically the diameter. Diameter, when we are talking about carbon fiber, is somewhere around 5 to 10 micrometer. Okay. The length can be, well, now you get this even smaller. So you basically get a single layer or several layers of carbon atoms. So the structure is even more special than carbon fibers. So they can provide higher mechanical strengths, heat conductivity, and the electrical conductivity. Yes. So all these things, and you can use this in the semiconductor. You can use this as conductive materials. To use this, also use this as sensors, and then to sense different temperature change or humidity change or different gases. So when the carbon nanotube has been used in many different applications. So once these things, you are using those things. So you have everyday wear and tear. So then the question would be, would these carbon nanotubes be released? And then the consumers are directly exposed to these. Will the carbon nanotubes go into the lung? And then once they go into a lung, so there are a lot of studies have shown that carbon nanotubes, because they are so long, so they are similar. They can cause similar effects as asbestos.
Wow. Okay.
So there are studies showing this. Of course, carbon nanotube is a very broad term. You have very soft carbon nanotubes which will roll up, and then you don't worry too much. But you also have relatively stiff carbon nanotubes. They are long and stiff, so they are similar to the asbestos. Once those things go into your lung, so you could also have lung cancer. So you can find thousands of papers doing this, the toxicity of CNTs. So one study, what we do is to look at these consumer products and these plastics where you have these carbon nanotubes or graphene or the other other nanoparticles in them when they are being used. So you need to cut those things, or there's some abrasion, you want to modify it, or somehow you put this there's an accidental fire or something, then these nanoparticles are being released. So the question is, what's the impact on the human health? And then we do this type of study, not with real human, of course, but then we do this, we collect the material, and then we have the lung cells with our colleagues, then we put these in the lung cells, and the biological studies, this can show you whether these things will cause the health impact or not.
This is very interesting because, as you said, carbon nanotubes, they have so many applications in semiconductors and in strengthening materials, but then there's also this downside to using them, because they look like the most feasible solution if you have such great properties.
Right.
But there's these problems, and it's very novel how science is also looking at what the detrimental impact of this new technology will be.
Sure, that's exactly what we do in the environmental engineering. So we need to look at this. You have the technology side, and also you have the environmental, the interface between the technology, the technosphere, and the biosphere, and then the environment. So we are looking at this interface, and then what's the impact of the advanced technologies and on the environment and human health. So this is the same thing when asbestos, 50 years ago, asbestos was considered as the magic material.
Yes.
It's so good, it has so good mechanical properties, and you cannot burn it. So it's considered to be a magic material, and now it's totally banned. So for nanotechnology and a lot of the studies on the societal, the environmental, the health impact of the nanotechnology is done right now, rather than similarly like asbestos. 30 years later, you see all these problems, then you regret you didn't do these studies from very early on. So that's
bringing back to air pollution, say Beijing or New Delhi, because that's in the news these days.
We all know it's pretty bad there. Like, if you go outside, you can really kind of feel it, and you see there's a lot of smog, you can't see very far. Why is it so difficult for those cities to cut down on air pollution?
That's a very good question. If I can answer that question in a couple of minutes, and then we will solve all the problem in China.
Okay, let's try to simplify this. So in Beijing, air monitoring systems have been put into use since 2013, and I was looking at data that shows that in China, ever since the air monitoring systems have been put up, the pollution has been steadily declining, whereas in India, it's been steadily increasing. And part of the reason is also because China has focused on improving the air, and China and India both rely on coal power so much, and coal thermal plants, of course, release lots of these harmful emissions. What do you think the problems arise? Is air monitoring a necessary first step?
Absolutely. The examples in America, the EPA, the Environmental Protection Agency, so they started all these so-called super sites, so to cover most of the regions in the U.S. So then they monitor the PM10, the PM2.5, Then the EPA set up the standards. Initially it was for PM10, and then later on from these studies showing the correlation was mainly for PM2.5. Then they strengthened the regulations on PM2.5. So the regulations are gradually. So you first need to monitor. You need to know what's the concentration, and then the regulators would need to gradually reduce the limit value. So in the U.S., so the PM2.5 was right now it's the annual average is 12 microgram per cubic meter. And then several years ago, I think the newest version is 2012. The previous one was 15, so they reduced that from 15 to 12.
And what's the regulation standard per year?
Like, at what point does it become really deadly?
So this I mentioned. So you have this linear relationship in the U.S. You have done this 6 city in linear relationship. So at that time when they did this 6 city studies, so they have this linear. I think this is 1990, maybe 1980 to 1990. So when you look at this, you have a linear relationship. So you don't really have a cutoff where you don't have like a step function. Below this value, everything is fine, and then above this value, everything is dead.
It's all linear. So like the more
in that range, it's more or less a linear relationship. So if you reduce this more, you have better health for the citizens. If this is increasing, it's not so healthy for you. So it's a gradual. It's not like somewhere you have a clear cut. But this linear relationship, all these relationships, all these correlations, they have certain applicable range. And then if the concentration in China is this linear relationship still applicable, most likely not. This cannot be always linear. So somewhere you have a saturation if it's too high. So to answer your question is I don't know if you have one value. So this value. So for example, in China, just for comparison, the U.S. standard is annual average. Annual average is 12 microgram per cubic meter. And then in Beijing now the annual average, I don't have the exact data, it's probably somewhere between 100 and 200.
Well,
so it's about 10 times higher, one order. And on certain days, on a bad hazing day in the winter, it could be 500. So you have 50 times higher.
Yes, I actually saw a report where China is now hoping that in the coming year, 2017, they will have about 203 or so sunny days where I believe PM2.5 emission would be on an average less than 100 micrograms. So that's really bad. So in order to mitigate the situation, as a scientist, since you look at it from a different point of view, where do you think investing the effort makes more sense? Should you be telling people, individuals, to make a change, or should the government be focusing at industry emissions or power plant emissions? Where does it make more sense?
What would have the biggest impact?
So, you have to, for air pollution control, there are a lot of different strategies, and this is a very complicated problem. It does not make sense, you say, that for the whole China, I have one single strategy.
Right.
So you have to look at locally what is the best, and then for different cities you have different situations. And in Beijing, as you mentioned, Beijing is a very special case. Beijing, if you look at the ranking of Beijing, China, they have, once they started this monitoring network, they have, you can look up the ranking of 300 different Chinese cities. Sometimes Beijing is ranked the worst. Sometimes Beijing is ranked as the best.
Well,
okay.
A lot of time is depending on the weather. if you have a very good wind, this wind is blowing in the right direction, so it will blow out all these from the industry-generated particles, industry-generated pollutants. So the wind will disperse all those things, and then everything looks very good. And then sometimes the wind is blowing in the opposite direction, and all these pollutants are all blown to Beijing, or especially in winter. In winter, you feel this inversion layer is relatively low. You feel the sky is kind of low. In the summer or in the autumn, this inversion layer is high. Then you can see the blue skies more often. And in the winter, even here, you can feel the air pollution problem is worse. It's always worse in the winter. And then to make this even a bigger problem, you have heating. In summer, you don't have heating for the residents.
Oh, right, yeah.
And in the winter, so suddenly you have a lot more combustion. You have a lot more emissions in the winter. So then the problem you need to look. So you need to have these measurement stations. You need to try to identify where these things are coming from. So for example, in Beijing, of course, there are already a lot of studies coming out. So what I say here, it's only I heard from all my colleagues. They do this so-called source apportionment. So you try to find out where the particles, where the emissions, where these sources are. So the sources are obviously the usual suspects: the transportation, the power plants, the chemical industry, the cement industry. If you have oil, you have petroleum refinement, all these things will generate. And then for Beijing, it's a rather special case, because in Beijing, they already, starting from many years ago, they already have the initiative to move the heavy industries out of Beijing. So now probably transportation in Beijing, I would guess, I don't have the data, my colleagues, I'm sure this data is available. I think probably the transportation is a significant contributor for Beijing. And then for some other cities, of course, Beijing said, I will not have all these heavy industry, but you still need the power stations where the electricity is from. All these things will need to go somewhere. So then the other cities around Beijing, then they end up with all these industries. Then for them, then then you look at the sources. So if you want to solve that problem, so you first need to do monitoring, identify the sources, and if the sources are the power stations, as the chemical stations, then you work with those stations. Then you treat the flue gases. You cannot allow the combustions just have a chimney and everything coming out. You can see the black smokes coming out. So 50, 60 years ago, that's what happened in the industry. Then now, for the development country, you don't see these chimneys with black smokes that often.
They install filters on the chimneys.
Right, there are very sophisticated the flue gas, the treatment system. So you can use all the different systems: the electrostatic precipitator, the baghouse filters, the wet scrubbers, the denox, you try to remove the NOx, the desox, you try to remove the SO2. So all these systems, you have very sophisticated technologies to remove all these pollutants.
Like they remove it and then they collect it into like a specific location, and they
there are a lot of different technologies. So part of this is, of course, as you mentioned, if you have a lot of particles, then you can, for example, the most simple thing, you put a filter here, and the flue gas goes through, the particles end up on your filter, and then a lot of stuff after a certain amount of time, then you need to collect all these particles. So quite likely these particles go to a landfill. And sometimes maybe you need to do something on that. You want to recover something and recover some metal or something, but after some certain treatment, most likely they end up in the landfill.
A question related to what you just said. You said usually it also depends on the weather. Wind comes in and it can blow the smoke away from the city, but the harmful particles, they still stay in the air.
No, after a certain time, they only have a certain lifetime in the air. Eventually they will settle down, and then but during their lifetime they already change. They might already attach onto bigger particles, attach onto other stuff. So the chemical composition could change, and their size could change. One most well-known effect is the rain, the washout effect.
Okay.
So after a rain, you feel air is fresher. That's clearly a lot of pollutants are being washed out.
Okay, just one concluding question then. What do you think is the fate of these nanomaterials in the future? Like we discussed about nanotubes as well. Are we going to just get rid of them, or do you think they still have a future?
I definitely think they will have a future. So the technology, it's like all the technology, they have their problems, but
the good outweighs the bad.
Right. You always need to have a certain balance, and most likely the people will continue to work in the directions. People will continue to discover new materials and then come up with new ideas. And so I definitely think this is a field where it's going to grow, and we just need to make sure that we understand the potential effect of these things. Usually for technologies, the first development is you try to solve the problems. You are worrying about the functionality of the materials first, and then after that you think about, okay, what's the impact on the environment, on human, on society of this development. I think certainly you cannot just throw away all the new ideas just because you worry about their potential impact.
Okay.
Great. Thank you very much.
You're very welcome.
Being on the show.
Yes, I got to learn a lot that I didn't know before. Thank you very much.
Yeah, my pleasure.
Thank you for listening. If you liked it, we'd really appreciate it if you shared it and gave us your feedback. We publish a new episode every week. For more details, visit our website simplified.xyz.